Okay, in this sixth and final installment of the basics of Newton's laws, we're wrapping up the idea of action-reaction forces. Again, it's not cause and effect. I can't say that enough times. It is, if you have a force, you must automatically have a reaction force that will be equal in size and opposite in direction. So, as you sit in the seat in a physics classroom, Earth pulls down upon your body with a gravitational force. The reaction force is the chair pushing upwards on your body with an equal magnitude. The question is that false or true? And if not, can we correct it? Well, let's look at the action force. Earth pulls down upon your body. That is the action force. Now, that means that the reaction force is, again, just to flip that phrase, opposite. Your body pulls up on the Earth. Now, our person postulating this said that it was the chair pushing upwards on your body. Those two don't seem to match, so I would say it has to be false. Okay. Now, this kind of tends to freak people out a little bit in terms of the Earth pulls down on me and I pull up on the Earth just as hard as the Earth pulls down on me. Well, how come the Earth doesn't come up and meet me? Why is it that I move down toward the Earth? Well, the forces between you and the Earth are exactly the same, opposite in direction. But the Earth has a lot more mass, which means it has a tremendous amount of more inertia. So it really resists changes in motion much more than you do. So you're the one who ends up accelerating and moving toward the Earth, as opposed to the Earth accelerating and moving toward you. If the two masses were more closely matched, you would see two different objects kind of moving around each other. So you can see that in binary stars and other types of astronomical situations. All right, Shirley Board sits in her seat in the English classroom. The Earth pulls down with a gravitational force of 600 newtons. What is the reaction force to the force of gravity acting upon Shirley? Now again, it's Earth pulls down, and we even have a number this time of 600 newtons. So again, all we really have to do is reverse that. So since Earth is pulling down on Shirley's body, Shirley, at least her body, pulls up on the Earth. Okay, and that size must be equal to the amount that was pulled down with a force of 600 newtons. Okay, so again, the forces are equal and opposite. The results are not, and this law is not about cause and effect. It's about the amount of force that occurs whenever there's an interaction between two objects. Okay, so we're going to fill in this and just be careful about making sure we apply a couple of the laws of motion at the same time correctly. The law of action-reaction says that, again, the force between the two objects must be equal in size and opposite in direction. The second law, the law of acceleration, says that the net force is proportional to the acceleration, and the mass is inversely proportional to the acceleration. So more mass, less acceleration; more net force, more acceleration. Okay, so we put a bullet in the rifle, we pull the trigger, the gun goes off. The force experienced by the bullet is. Now, again, the force must absolutely be equal to the force experienced by the rifle. The two experience exactly the same force. But the bullet has much less mass, and therefore its acceleration is greater than the rifle. The rifle will go back, but at a slower rate of acceleration because of the much larger mass. B, the bug crashes into a high-speed bus. The force experienced by the bug, again, there's no option. The third law, the law of action-reaction forces, states that the force must be equal to. I don't need to think about this. It has to be equal to the force experienced by the bus. Now we're going to see the bug probably get squished. We're going to think, ooh, the bug got hit so much harder. But it's not that the bug got hit so much harder. It's that the small mass of the bug means that it suffers a much greater acceleration than the bus. The bus barely even notices the bug. Now, if you had a bus run into 1,000,000 bugs, you would actually see the bus being slowed down by hitting all of those bugs, because each one would do a little bit of deceleration of the bus. C, a massive linebacker collides with a smaller halfback at midfield. You should be sick of this one by now. The force experienced by the linebacker is equal to, forget making any choices, the force must be by the third law of motion. The law, scientific law of action-reaction, must be equal to the force experienced by the halfback. The resulting acceleration of the linebacker, the linebacker has more mass, therefore the acceleration of the linebacker will be less than the acceleration of the halfback. So you might see the halfback get flung back. It looks like, oh, the halfback got hit so much harder than the lineman or the linebacker did. Again, the forces are equal. The results are not necessarily equal. This is not cause and effect for the third law. It's only the forces must be equal and opposite. Finally, on a pool table, a 10 ball collides with a 14 ball. Assume they both have equal mass. The force experienced by them, again, must be equal to. There's no choice. And because their masses are equal this time, their accelerations would also be equal. In fact, you might see one stop and the other move on, taking the same velocity as the first one had. So if the masses are equal, the resulting accelerations will be the same. Again, we see, this is where the misconception comes in. You see that small thing get crushed, you think, oh, the forces must be much greater on it. You have to think deeper. The forces are equal, then the changes in mass, the differences in mass, cause the resulting change in acceleration, which is higher, and therefore creates the bug being smushed, crushed, thing broken, whatever it may be. Okay, so there are multiple things going on here at once, and you have to be able to deal with all of them. So it's a pretty complex thought process. It takes time to get used to. The simplest element should be that the force is always equal whenever two objects interact.